Hello, my name is David, and as my final project, I studied the physics behind lateral deflection of a spinning ball that travels through the air. The phenomena that causes this is the Magnus Effect, suggesting that a spinning object moving through a fluid deflects from its straight path because of pressure differences that develop in the fluid around the object. How these pressure differences occur is explained by Bernoulli's principle, stating that an increase in the speed of the fluid occurs simultaneously with a decrease in pressure, and it works vice versa too. So how this works in case of a spinning ball that travels through the air is following. The air travels in so-called stream tubes, which are defined as the area between two streamlines of the air. As these streamlines collide with the spinning ball, more stream tubes are dragged around the side that is turning with the airflow than around the side that is turning into the airflow. In this case, what this causes is that the air flows faster on the bottom side than it does on the upper side. So the pressure is eventually lower on the bottom side than it is on the upper side because of Bernoulli's principle. And the net result of this is that the air is deflected sideways. In the case of this video, it is to the bottom. So you can see as the air is dragged around the side that is turning with the airflow, it's dragged to the bottom in this case, while the airflow in this side is retarded by the rotation of the ball. And as these two airflows meet, the net result is that the air is deflected to the bottom, and because of Newton's third law, the air must exert an equal opposite force on the ball, which is in this case to the top, and that's the actual Magnus force. The formula for Magnus force is following. So we can see that it's directly proportional to lift coefficient, density of the air, cross-section area of the rotating ball, and velocity of this ball. In my experiment, I tried to simulate the Magnus force by simulating the flight of the rotating ball through the air. By using a fan, I simulated the air's velocity, which is the same as the velocity of the ball, and by using a string which I twisted and then I released it, I simulated the rotation of the ball. However, even though in my case the ball should have deflected sideways, it didn't happen, as you can see in this video, which was pretty much the same in all of my trials. And the reason for that is the following. When I tried to calculate the actual Magnus force, I found out that the Magnus force experienced by the rotating ball in my case was around 0.0209 newtons, and under such small force, the angle in which the ball would have deflected would have been probably around 0.01 degree angle. So what I found out is that for the ball to experience significant sideways lift side force and to have significant sideways deflection, the ball must travel in a relatively high velocity.